Okay, so I'd like to talk to everybody about what we call an AI operating system. I start with a bit of a motivation and try to explain why we need to focus on building a new type of operating system. You might have noticed that AI's space have evolved considerably in the last few years, and how we use the large language models has also evolved a lot. We started with models that we used to generate text, generate images. So essentially, then in that era, although it's an exaggeration because we are talking about something that has happened probably about 3 years ago, the model was the primary interface with which we have interacted. We have moved to AI that can chat for you, so with various levels of assistance. And now we are at the level where we actually we are building agents that we want to do things for us. That is demonstrated by products such as Claude, Cowork, or OpenAI Frontier, but also by emerging open source technologies such as OpenClaw, Hermes, and others. So the question really is, what does evolution of these types of applications mean for platforms that we need to build? We are saying that what it really represents is a new wave of platform evolution. When you look historically, the evolution of computer science have went through these kind of 3 phases. The first one started when in the 50s, 60s, when the industry, when the field came to the realization that we need to separate software from hardware. And that led to the evolution of high-level programming languages such as Fortran and COBOL, and obviously entire generations of new languages that emerged afterwards. And to support these applications, operating systems were built. So this is the first time when the concept of operating system was created, and operating system provided a place where these applications can run, and it provided a set of basic primitives through which these applications could interact with hardware underneath. In the 90s and 2000s, we went through the phase of distributed or cloud operating systems. And here the motivation was that we started to think about reuse, how we can connect services and applications running potentially in different parts of the world seamlessly with each other. That obviously created new protocols, entire new stacks of applications, and led to the creation of distributed operating systems, of which clouds have become the best realization. And the motivation was, and the kind of primitives that we focused were, being able to discover services, connect to these services, scale, provide resilience, and implement transactions. What is happening now is a new wave, and it is dominated by the fact that we want to build these AI agents, make them safe to use and run. The interaction model, the language in which we program these systems, is human language. We do it through prompts, instructions, and skills. And the operating system that needs to emerge will need to deal with challenges that these applications bring about, many of which we are discovering still, but they most likely are going to concentrate around helping these applications become more resilient, more secure, and also more secure and safe in their interactions with the external world. All of this is really driven, when you look at this historically, by the need to improve the speed of innovation. We essentially implement all of these various transitions because we want to innovate faster. When we look at how agent is defined from the perspective of AI community, there's actually a lot of debate. So agent is an autonomous system that can use tools and collaborate with other agents. There's debate about its, how deep it should be in the areas of reflection, autonomy, ability to refine its own tasks. So essentially, at which level something that is not an agent becomes an agent. But we are going to leave that debate aside, and we look at it from the perspective of the system. And from the perspective of the system, An agent is an application that leverages LLMs and interacts with classical components to realize a business function. And it differs from the classical application in two ways. First, it exhibits intrinsic stochastic variability of outcomes. And the second key distinction is that the expectation of autonomy are exceeding that what was expected of regular cloud applications. And these two properties make these applications particularly challenging to run reliably. Agents exhibit a very well-known and quite established pattern. It's a piece of code that is driven by some instructions or skills and interacts with large language models to define what the next step should be, with external world, so the concept of tools, and it maintains state in something that is loosely called as memory. This code, so the center of the agent, can be written in a variety of ways. There are multiple design patterns that can be implemented from RAG, React, Planning, Reflect. All of these can be provided here. And it can be implemented in a variety of frameworks, LangChain, LangGraph, or no framework at all, pure Python. It can also be implemented by various generalist harnesses, such as Claude Code, Hermes agent, and others. So regardless of actually there's a lot of diversity in how these agents are implemented, but regardless of how that's done, this pattern actually endures. Now, agents are fundamentally unreliable, and this unreliability can come from a variety of sources. They can by pure determinism, they can violate constraints that have been imposed on them. They can lose context, lose memory, also through a variety of reasons. In multi-agent systems, miscoordination between agents may happen. So one agent may withhold information from another agent and provide the other agent with incorrect information. Verification in agents may fail. So agents can finish tasks before actually these tasks are the requirements are fully satisfied. They are generally unable to self-check themselves. And in multi-agent systems, errors cascade. So sometimes a very minor issue in one place can actually escalate over multiple steps to become a serious failure. Now, when these agents interact with the external world, they are creating durable results which may violate principles that we normally want to observe in the real systems. We have no rollback, we have no transaction guarantees. So the effects on the real system may actually be very profound. So we can have transactions executed that are irreversible but not correct. We can have duplicate transactions being executed, conflicting actions taken by different components, corrupt, wrong outputs propagated to databases, APIs, and users. And of course, we can have this silent propagation of various failures through multiple steps that are hard to detect because we don't even know where these problems originated. So over the last months, I think is the right way to say it, the realization has emerged that you cannot really fully fix the agent by fixing large language model. It has been demonstrated that mechanisms for self-correction without external feedback are not working very well. Agents tend to still degrade in performance. Self-detection has proven to be very unreliable when it comes to LLMs alone. Errors take to compound, which I've stated on the previous chart. They can propagate to memory and as a result propagate to future decisions taken by the agents. And agents have been demonstrated to be very good in concealing failures when they get pressured. So what we've seen is that those who are successfully deploying agents in production systems where these agents are actually able to execute on a real world tend to invest a lot into scaffolding and harnesses that are that surround the LLM and make the outcome more reliable. So you can see that in both in research work, but also in systems that are available in production. Of course, Claude codecs, which we are all using, are based on our realization of the harnesses. There are other practitioners' reports about systems like Manus, Versal, Spotify, that all invested very heavily in implementing those harnesses and scaffolding that implement reliability, resiliency functions around LLMs. So agent today is not an LLM. Agent today is LLM plus a harness. That harness implements what is called an agent loop, but it performs a variety of other tasks such as context management, so assembly, summarization, compaction, essentially decides what information should actually be fed into LLM. It decides on what should be remembered, so on memory formats. It performs structured data handling or any kind of deterministic tasks that are easier done in code than with LLM, and performs evaluation and failure detection. But we are also seeing is that, and in fact, the emergence of harnesses already represents the shift from all the intelligence and action being done by the model, shifting it outside to the code surrounding the agent and to the platform. So we also see the emergence of platform capabilities around lifecycle management, identity and access, tool registries and skill registries, connectivity, routing, and of course the emergence of protocols such as MCP and A2A, which demonstrate this need to extract some of the intelligence and logic into a more standardized and reusable platform components. So sometimes it is called externalization, but I think the key premise is that there is going to be a need for primitives that help LLM-driven applications to achieve reliability, security, and efficiency in a more generic sense in the real world. Now, these arrows represent the shift that is happening from model to platform, but you need to acknowledge that models are also going to improve, so the boundary is not defined, and it's going to be debated over the next months, I think. Now, one of the ways in which the capabilities are shifting from model to platform is the emergence of cloud-native harnesses. When you take the harnesses that we work with today, they are all monoliths, right? So they encompass all these functions that I mentioned, context management, state management, within a single blob of code. When we try to move them to cloud, obviously we violate all the benefits that cloud was typically bringing to the application. So we call it sometimes lift and shift, because here the session management, the state management, everything is buried into this monolith. So we lose the benefits of scalability, resiliency, recovery. All of these properties are violated. So we begin to see the emergence of cloud-native harnesses. Cloud-native harnesses externalize the components that parts of the harness into separate layers. So state is getting externalized, execution capability is getting externalized, and of course models are externalized already. That gives us all the benefits of cloud, of distributed platforms, scaling to zero, the ability to shut down an agent that is not in use and waiting for response for a long time. We get cold start capabilities, and of course we have much improved resiliency. So what does the cloud-native harness look like? It's a serverless pattern that runs a harness as a stateless serverless container, which can interact directly with the LLM, that externalizes a state in this state we're talking about context into a durable session log that persists, of course, between the executions of the harness, and it externalizes the execution of tools into the execution sandbox. So now we can achieve the security because execution is actually happening in the sandbox, and that security can be adjusted to the specific needs of the agent. We don't have to package the entire agent into a sandbox, which normally would be a virtual machine. There are multiple examples of such architectures that have emerged. We see that happening in Anthropic, the cloud native Claude in managed agents is actually executed according to a similar pattern. Meta has invested in similar technologies, and we see the emergence of similar ideas in open source communities as well. Now, there are other examples in which of places where those primitives, AI operating system primitives, are emerging. One of them is the evolution of protocols. So to me, the fact that MCP was proposed and then A2A is really an attempt to externalize the idea of and separate the execution of tools from the execution of the agent, and this way provide a more standard mechanism for interacting with the tools. So the MCP has become one of the key ways in which agents can interact with the external world, but it's definitely not the only way. The CLI-based and API-based techniques are also used by many agents. So we believe there's going to be a range of various protocols that are going to be used. Nevertheless, MCP remains the most popular one, particularly if you want to integrate external tools with agents that already exist. So around the MCP protocol, last year brought us this large number of MCP gateways. And that's again a way in which a platform can control how tools are being invoked. MCP emerged to provide easy access to tools and easy discovery of tools. But it comes with lots of issues. First of all, there are lots of MCP servers. They can come with just connectivity becomes problematic. So MCP gateways emerged as a mechanism to provide single access points, so you can discover MCP servers from that access point. Here is when you have aggregated catalog, discovery, you have routing, but you also inject various security safety functions such as authentication, access control. You can control visibility of these tools. So in production deployments, enterprise deployments, MCP gateways have become a key element of the platform to manage connection between agents and external world. Another crucial problem to solve here is that of identity and authorization. If agents are to be autonomous, people need to have control over what they can see and what they can do. Standard authorization and access mechanisms that exist, they were built for an interaction in which a user is sitting in front of the browser or a mobile application, and interaction pattern is known a priori. So you have this chain of logging in, obtaining a token, and the token is propagated and exchanged through the steps of interaction. But in agentic world, the invocation pattern is not known a priori. Agent decides what is the next tool they want to call. So it is not possible to realize this the same safety approach with the same guarantees using these standards. So what we need to do in order to ensure that agents can act according to the same least privilege mechanisms as human employees today is the concept of identity. We need to be able to identify agents based on what they are and what they can do. So we need to associate agents with this digital identity, and then based on that identity, allow humans to grant agents delegated access to external tools and services. And of course, identity needs to be attested by a trusted authority. You can begin solving this problem using existing technologies, such as SPIFFE Spire. This is for workload identity, but it allows us to identify an agent. The proxying technologies to discover that identity and to perform authorization actions on behalf of the agent. Obviously, IDPs, such as in open source, it's Keycloak, but of course, there is a large number of those IDPs available. Standards such as OAuth2 and token exchange that allows us to implement delegated access. Technologies like OAuth1 providing more advanced access policies such as attribute-based access control, and leveraging Kubernetes sidecar parent. So at least in our projects, that's what we have been implementing, and it gives us a good starting point for controlling what agents can do. But that doesn't solve all the problems. What we can do with existing technologies is attest and authorize workloads. In order to identify and authorize agents, we need to increase the level of semantic understanding. So we need to understand what agent is not just based on what its image and Kubernetes identity. We need to know its identity based on what it can actually do. We don't have a good answer to this question. Maybe it's agent card, maybe it's something that we need to derive from context, but that problem remains to be solved. And together with this, the unsolved problem is that of attestation. So how do we guarantee that the agent is actually is what it claims to be? Is a signed agent card sufficient, or we actually need to do runtime discovery? And authorization, of course, cannot be based only on scoped tokens. Authorization needs to include other aspects, such as semantic analysis of agents' behavior. One example of that is that we have been experimenting with is the providing access control based on intent of the agent. So essentially validating that what agent is trying to do is actually aligned with the intent of the user. Another category of problems that are brought into this space is that observability. Point-to-point observability that we can do in classical cloud systems are not sufficient. And that is because of this propagation of problems that between various components and what the agent is going to do in the end. In this particular example, we have an agent that is trying to decide if an order should be put in place. But what happens, the agent is deriving information from the vector database that is indexing historical inventory orders. And the failure in that system may lead to stale data being presented to the agent. Based on stale data, the agent, otherwise working correctly, is going to create an incorrect outcome, and it's going to place an order that should not have been placed. So in order to understand the behavior of agents in the systems, we really need to think about observability in an end-to-end manner. Now, a question here is, there are actually multiple questions, and one of them is, what is actually the right unit of observability? What should we be paying attention to? An agent, entire trajectory of execution, a distribution of the trajectories, so not a well-answered question. What is actually a failure? HTTP 200 is not a good answer here. Because answer may be the response may be returned, but the answer is incorrect or unsafe. Why failure happens? So here we're talking about the attribution of failures, where the problem originated, how the problem propagated across the system. And finally, how do we implement it at scale? All approaches that we see so far focus on collecting the data from the entire execution of the agent, but that amounts to a lot of data. So how that data should be managed and how we actually scale a system that can identify and manage agent problems is an unsolved problem. Now, a lot of times when we try to improve the agent, we are talking about improving the prompt. But the world has already moved from prompt engineering to context engineering, and we believe it is not the final answer. So in prompt engineering, you provide a prompt. If the prompt is not correct, you improve the prompt, and so on and so forth. Essentially, all the onus is on making a good prompt so that the agent can produce a good outcome. And of course, the burden there is not on the user or developer. Context engineering has moved this away. So what model, it decides what model sees and what across multiple calls, and it's done in this harness or scaffold around the agent. Key problem is what to keep in the context, when to compact, when to summarize, and the burden is on the developer of the harness. That requires a lot of expertise and a lot of domain knowledge to do it correctly. That's why we believe that in order to scale and allow lots of people to implement viable agents, that needs to evolve and become more standardized through some primitives so that a broader group of people can actually implement these harnesses. So what is next? We believe that there is a need for more platform-based mechanisms for managing context that would decide what information is critical, that would allow to provide contracts, such that critical information is retained in the context versus non-critical information being offloaded. And of course, this would help us to capture violations that may be happening in that area. So if the agent is presented with the incorrect information, we would be able to catch it on the platform level. Now, we are implementing many of these primitives or experimenting with them in the context of an operating open source project. If I go back for a moment to this three phases or three waves of evolution, we can see that they actually ended up with standardizing on specific open source platforms. The classical operating system over the decades ended up with standardizing on Linux. In distributed operating systems, Kubernetes emerged as that standard platform. So we are asking the question what that new standard platform will be. We believe it is going to be built on Kubernetes or existing standards, but the question is, what it's going to be and what primitives it's going to have. Now, I make no pretense that Rosso is going to be that platform, but this is the place where we are experimenting with these primitives and trying to implement some of them. At the core of Rosso, we have what we call Rosso Cortex, and that's a controller that surrounds the agent with in the form of sidecar technologies with various primitives that help us to control and observe what that agent is doing. So as I said, it is a type of sidecar technology with a variety of implementations that intercepts every single interaction that agent has with the external world. So inbound and outbound connections from between user, the agent, LLMs, and external world are captured here. So that allows us to see everything that the agent is doing and all information that the agent is receiving. We are implementing several technologies that are, or several capabilities as a part of that controller. No question, it was just noise, right?
1 minute left.
Okay, 1 minute, okay. So among these primitives, identity and access control, which I touched upon a bit in this discussion, guardrails, so input-output checks, policy enforcement, tool reflection. So if an agent calls a tool, can we evaluate the tool for its coherency, correctness, alignment with what the agent is intending to do? Context optimization, so compressing, prioritizing data that should be in the context. state management, so capturing persistent state and persisting that state for recovery, and crash recovery, so checkpointing, resuming, and similar functions. So that was a very brief overview of what we are doing and where I think the industry is going. And I think there is a lot of interesting work to be done by the scientific community. Since this is a serverless forum, I was trying to highlight a few of these. So in the serverless pattern where state is externalized, the key question is, who manages the what agents can see, how you manage it, how you develop a contract between agent and the platform that is going to manage the context, managing the context window size. So the state is constantly growing for agents, minus summarization and the compaction, the context is growing. So it is different from what we were seeing in classical serverless workload. So how you manage that is an interesting problem. Observability, which I described, we need to deal with semantic correctness, a semantic observability, not just structural. Sandboxing at scale, so we are going to, if execution happens in various sandboxes, then we're going to have lots of sandboxes that need to be started per invocation or not. What is the cost? Authorization, as I mentioned, must be context-aware and dynamic, and understanding failures in such a system. So where problem happens and what needs to be fixed also needs to be addressed. With that, I'd like to close. I'm happy for any questions and discussion.
Thank you. Do we have questions in the room or online? If you have questions later, I will send them to Gosia if you put them in Discord.
One question. So generally for Alec, can you listen to a question from here?
Yes, go ahead. Just come closer to microphone.
So generally for operating systems, it has always been that we take thoughts and we generally operating system help thoughts into actions, right? So we have a thought of doing a multiplication, operating system helps us do that in hardware. Now, if you are moving to AI operating system and the idea of AI has been mimicking human thinking, shouldn't the idea of AI operating system would be the same way to, like the way we mimic human accountability? Like for example, for observability, maybe we can implement something along the line how a manager checks work for your employee, right? Doing checkpoint, making sure you are with your objectives. Same thing with the, like dealing with LLM agents. Humans can formalize that these are my XYZ tasks, and LLM can every time validate this XYZ task are doing. Like basically mimic the way we manage humans, we'll manage the AI in that way while we're designing AI models. Would you say that?
So yeah, so that's exactly right. Although I wouldn't necessarily compare an agent to a human, because the different mechanisms may apply. But in principle, I agree with you that what we need is the mechanisms to evaluate what agent is doing based on some contract, some policies. I don't want to overuse the word of policy because it has lots of meanings, but yes, there needs to be some guardrails, some policies that govern what the agent is allowed to do, and also evaluate the agents or audit the agents after the fact if they have actually performed actions according to to goals, if you will. But I think the problem still remains that if agents are, and we want agents to be as autonomous as possible, right? Because that's where the value is. And we want them to be non-deterministic because that's also where the value is. Then the problem remains how we avoid and prevent irreversible problems from happening if we apply these agents to business or mission critical tasks. So what you are saying, having the way to policy and evaluate is an important problem. Essentially, we don't have a mechanisms today to do it in such a way that we allow the agents to perform the work and actually give us value while preventing irreversible changes or irreversible actions from being taken.
Thank you.
One more question here.
So I would like to ask, like you talked about externalizing, for example, states, and in general, making the work due to like other external components. Like for example, in the operating system, when the kernel code runs, it remains within the kernel boundary. So would it be more meaningful to internalize operations like state management, for example?
Yeah, so I would, if I were to, play further with the operating system analogy, I would say in agent world, tool call corresponds to system call in the operating system. Okay, and you have a clear way in which when you cross the boundary between the program in the classical world and the system call, you have mechanisms by which can happen, and you have a clear boundary that controls what can be done by and by whom, right? We're talking secure Linux, AppArmor, capabilities, all of this, right? You have these mechanisms. So what are these? So for agents, these mechanisms evolve as well. Actually, in this space, the world is a bit more mature, right? Because we have this MCP gateway, so we have a protocol, so we have a standard around with which you can work, and you have mechanisms around the standard, such as MCP gateways, the sidecars that we've been working on, and so on. So I don't know if it answers your question, but I think here the analogy is relatively clear, and I think the mechanisms exist, but we still do not have a way to achieve that on a semantic level. So if the agent is performing task that has been perhaps allowed because authorization exists, but the task is not aligned with the goal, that we don't necessarily know how to do.